Very good morning to everyone. Today's subject of discussion is protection of aldehydes and ketone, the strategies utilized. The aldehydes and ketones are protected from reacting by using the form of either acetols or 1,3-dioxylanes or 1,3-dioxanes. Let us look at the reagents and the reaction conditions that would be utilized for converting the aldehydes and ketones to acetols, dioxylanes, and dioxanes respectively. An aldehyde or a ketone, and I treat with methanol in the presence of an acid like HCl. The lone pair of electrons on the oxygen of the OH group of the methanol attacks on the carbonyl carbon, and the pi electrons moves onto the oxygen to become OH, and the another molecule of methanol reacts with the alcoholic form of this ketone in the similar fashion, and OH gets kicked off in the form of water molecule to give acetols or diacetols, we can call it as. And this is how we can convert an aldehyde or ketone to give acetols, and this is the one of the very versatile method of protecting the aldehydes and ketone from further reactions. They can also be protected in the form of dioxylanes by reacting with 1,2-diols. The OH lone pair of electrons attack on the carbonyl carbon, as we have seen in the way diols reacts with the aldehyde or ketone, and it gives rise to dioxylanes, and this reaction also occurs in the presence of an acid like HCl or H2SO4. We get 1,3-dioxylanes. It can, when we use 1,3-diols instead of 1,2-diols, we can get dioxanes. This reaction also undergoes in the presence of an acid as a catalyst, similar to that of dioxylanes, and also formation of acetols. The lone pair of electrons on the oxygen of the OH attacks on the carbonyl carbon, and the pi electrons moves onto the oxygen to make it OH, and the other OH group lone pair of electrons are shared with carbon, and it loses as water molecule, and it gives 1,3-dioxanes. They can be. This is another versatile method of protecting the aldehyde or ketones. In overall, they can be most versatile methods are protection in the form of acetol, 1,3-dioxylanes, and 1,3-dioxanes. This can be cleaved easily. 1,3-dioxanes cleavage rate will decrease when there are substitution on the dioxanes group. If there are no substitutions on the dioxane, it is more easily cleaved. When it is substituted, as we have seen here in this fashion. Ketols formation of alpha beta unsaturated carbonyl compounds is lower than that of the saturated compounds, because of the fact that the carbonyl compound adjacent to it, there is a double bond at alpha and beta position. That's why they are more stabilized. More is the stability, more difficult is the reaction to undergo. If I take a compound with a ketone group which is saturated ketonic group, and here there is alpha beta unsaturated ketone, if I treat with diols in the presence of an acid, the saturated ketone is protected more easily than that of alpha beta unsaturated ketones. Again, as I said, this is attributed to the resonance stabilization by the double bond present in the alpha beta position. Aldehydes are generally protected as well as ketones in the cyclic or acyclic ketol or acetal forms. They are stable to bases. Let us look at the cleavaging reagents that are used for deprotection of the acetals, dioxazines, and dioxanes. Deprotecting agents for acetals used are acid catalyzed hydrolysis. This can be achieved by using aqueous acids like perchlorate, Lewis acids like zinc bromide, and strong acids like trifluoroacetic acid in water. The aqueous acid, strong acids, and Lewis acids. All these acids can be used for acid catalyzed hydrolysis. They can also be cleaved easily by using oxidizing agent which are mild in nature like iodine in methanol or potassium peroxymonosulfate. Let us look into the deprotecting agents used for deprotecting the 1,3-dioxalanes. In the similar fashion to that of acetols, they can be hydrolyzed by using strong acid like perchloric acid. This can also be cleared by using acetic anhydride and it gets converted into the form of allyl alcohol acetates. The deprotection can also be brought by using oxidizing agent like hydrogen periodate or periodic acid, and it can be accomplished by using the reducing agents like lithium aluminum hydride and by using Grignard's reagent where the nucleophilic attack takes place and gets deprotected. Special catalytic agents like sodium tetrakis 3,5 trifluoromethyl borate in water can be used. The beauty of this catalytic agent what we use is the reaction can be taken place in the presence of a polar solvent like water. Dioxins can be deprotected by acid hydrolysis. We can use aqueous acid like HCl and H2SO4 similar to that of acetols, but this cannot be achieved by using Lewis acids. It can also be hydrolyzed by using base as the catalyst. Lithium tetramethyl pieriodide in THF is used. Specific catalysts are also used for deprotection of 1,3-dioxanes. One of the best catalysts used is trimethyl chloride and sodium iodide in acetonitrile. Another specific catalyst which is used for deprotection of 3-dioxanes is sodium dodecyl sulfate SDS and iodine in water-based medium. As this is water-based medium, this is more eco-friendly. These are the methods of deprotection of aldehydes and ketones. The aldehydes and ketones can also be protected in other forms. Before going to that, let us look into the cleavage of the ketols. If I have 1,3-dioxalane and 1,3-dioxanes as shown in this molecule, I can use lithium borofluorate and I can cleave the dioxanes in the presence of dioxalanes. When I have both dioxalane and dioxane and I want to cleave only dioxanes, then I use the special reagent lithium borofluorate. When I have A ketone or aldehyde treated with this diol, which is attached with methyl sulfonate. This type of oxalanes are formed, and for this type of oxalanes where it has a CH2SO2 pH attached to this dioxalane, I use DBU and DCM to cleave. DBU is 1,8-diazo bicyclo 540 andexavenine. This is a non-nucleophilic base which we use, and DCM is the solvent used, dichloromethane, and these are the special reagents used for special reaction conditions. Lithium tetrafluoroborate can be used to preferably cleave dioxane in the presence of dioxalanes. When nucleophilic bases do not work out, we can use this non-nucleophilic bases like DBU. We can also protect the aldehydes and ketones by forming 1,3-dithiene derivatives. For obtaining this 1,3-dithiene derivative, I'll take a ketone or an aldehyde and treat with 1,2 dithiols or 1,3 dithiols, and we will get corresponding dithiolanes and dithioxanes. That's why they are generally called as dithienes. The salient feature or the beauty of 1,3-dithiene derivatives is that aldehydes can be selectively protected in the presence of ketones. When I have both aldehyde or ketone, I want to protect only aldehydes and leave the ketone unaffected. I will protect in the form of dithienes by using either 1,3-dithiols and or 1,2-dithiols. And the reagent used is dithiol in the presence of boron trifluoride diethyl ether and DCMS solvent at 25 degrees centigrade. At room temperature, it can be formed easily. Another salient feature of protection of dithienes is that if there is an alpha beta unsaturation adjacent to the ketones or an aldehyde, the double bond does not migrate to next position as we see in the case of dioxanes or dioxalanes. Dithienes, when I protect the alpha beta unsaturated ketone, the alpha beta double bond do not move to the next position. Whereas when I protect in the form of dioxalanes, the alpha beta unsaturated double bond has been moved towards beta gamma position. When this movement is not required, we go for protection in the form of 1,3-dithiene. 1,3-dioxalanes and 1,3-dioxanes which are formed can be converted into 1,3-dithiolanes and dithienes easily by treating with corresponding 1,3-dithienes or 1,2-dithiolanes. The boron trifluoride diethyl ether can be used as the solvent. Then be cleaved very easily by using mercuric perchlorate. Is using methanol and chloroform of the solvent at room temperature. It can also be cleaved by using N-bromosuccinimide and acetone as a solvent at 0 degree centigrade. I can also use a mild oxidizing in iodine, like iodine in the aprotic solvent like dimethyl sulfoxide. It can be oxidatively cleaved by using steric ammonium nitrate in aqueous acetonitrile. The cleavage of dithions can also be achieved by using metachloroperoxybenzoic acid in acetic anhydride, or by using 2,3-dichloro-5,6-dicyanone 1,4-benzoquinone, that is DDQ, in aqueous acetonitrile. Overall, summarizing, the aldehydes and ketones versatile methods of protection is in the form of acetols by using methanol and HCl as the protecting reagent, and can be cleaved easily by using aqueous acid like perchloric acid, Lewis acid like zinc bromide, strong acid like trifluoroacetic acid, and also by using a mild oxidizing agent like iodine in methanol. The salient feature of this protection as acetol is that these acetols which are formed are stable to bases, and also they are stable in neutral condition. That's why they are protected by using deprotected by using oxidizing agents or acidic agents. 1,3-dioxylanes protection is possible by using a protecting reagent like 1,2-diols. These are also stable to acidic and neutral condition as that of acetols. That's why they are also cleaved by using the strong acid like perchloric acid, oxidizing agent like periodic acid, a reducing agent like lithium aluminum hydride in the presence of acid, or by using Grignard's reagent, or by using anhydrides. They can be protected in the form of dioxins by using the protecting reagents like 1,3-diols. Similar to that of dioxins and acetol, they are stable to neutral and basic conditions. And this dioxins which are formed adopts a stable chair conformation. They can also be deprotected in the similar fashion by using acid catalyzed hydrolysis like aqueous acids like HCl and H2SO4, and the specific catalyst like trimethyl silyl chloride and sodium iodide in acetonitrile, sodium dodecyl sulfate and iodine in water-based medium, though it is stable to basic conditions by using these special bases like lithium tetramethyl piperidine in can be used in THF, and they can be hydrolyzed by using these special bases. Last method of protection of aldehydes and ketones is 1,3-dithions or 1,2-thiones or thiolanes by using 1,2-dithiols or 1,3-dithiols as the protecting reagent. The beauty of these dithions is the fact that the aldehydes are selectively protected in the presence of ketones. They are deprotected by using mercuric perchlorate in presence of methanol and chloroform at 0 degrees centigrade, N-bromosuccinimide and acetone at 0 degrees centigrade, and mild oxidizing agent like iodine in the presence of aprotic solvent like DMSO, using a oxidizing agent like steric ammonium nitrate in aqueous acetonitrile, meta-CPBA and DDQ. This is all about the protection and deprotection of aldehydes and ketones along with their salient features I have mentioned over here. Four methods are there in summarizing everything. And in the next presentation, let us deal with the protection of other functional groups. Till then, have a nice day. Thank you.